This presentation focuses on the application of Keel technology in the anti-AXS space, primarily to respond to threats from invading autonomous aerial vehicles. I will be briefly introducing the problem, the players, and the objectives of the anti-AXS system we will be demonstrating. The Audi commercial running in the upper right corner of the screen highlights the problem. The reason we are addressing the problem is because it is obvious that autonomous systems will be used as weapons. You could even say that the first arrow used in combat became an autonomous system the instant it left the bow. The evolution of technology suggests that these systems will operate without humans directing their every move. They will come in all shapes and sizes. Just look at what is available today. They will be capable of carrying all kinds of payloads. They will be intelligent enough to self-organize into groups or operate with full independence. They will be massively deployed by organizations of any size because they can be cheap and disposable. Think of them as a new form of smart bullets. So what does the new battlefield look like? The warriors are expendable. Where you may have to convince a suicide bomber to strap on the suicide vest and die for a cause, the new autonomous systems can be given a collective goal with policies that direct their behavior and released. If time is money, it will cost very little to convince an autonomous system to give up its life. The new autonomous systems will also use all the tactics and strategies that humans have collected and used throughout the ages. It is a new battlefield. I can only suggest that responding to these types of threats will be a continual never-ending process where technology competes with technology. And the best technology will win. At less than $1,000 a copy, almost anyone can play. As hobbyist and educational institution-developed capabilities are released into the public domain, group behaviors for autonomous systems will be downloadable from the internet. Even for individual players, the different players will have different goals, so there will be an abundance of tactics and strategies used by the autonomous systems. We had a meeting at CompSim's location to conceptualize what an anti-AXS system might look like. We focused primarily on a system that would respond to incoming unmanned aerial vehicles, as these appeared to be the most likely invaders today. With the previous slides painting a picture of the problem, you might look at this slide and the next as the marketing requirements for an anti-UAV solution, which I will refer to as the system. So we started out saying that our system would probably be connected to some command authority that would define the mission of the system and provide additional intelligence that could be used in situation awareness and decision-making for the system. We said the system would have sensors to recognize an invasion and understand its surroundings. We recognize that a single approach would not satisfy all possible scenarios. And along the same lines, all approaches would not be available at all deployment sites, and that during an invasion, resources would be depleted, so the system itself would have to be able to automatically adjust to change in capabilities as well as invasions of different types. We also recognize that there will be almost a constant evolution in capabilities, new responses, new sensors, and new information sources, and new capabilities utilized by the invading UAVs. In other words, the system must be easy to change. And then, from the legal, political, ethical standpoint, the system must be able to respond with the appropriate level of force. This is a critical element for any autonomous system, because while one may be able to argue the appropriateness of an action in a court of law, the term appropriate does not mean anything to our system. So appropriate needs to be translated into a mathematically explicit value. Continuing on, we said that the tools need to be used in the best way, which means that our system will have to adapt. We said that our system will have to be able to offer warnings to the invaders, as well as to be able to engage them according to the policy we develop. We said that our system will also be an information source to the command authority. We said that our system would have to accept new and revised missions from that command authority. We knew that once our system is deployed and it took some action, then someone will want to perform an after-mission review. This would be just as important for our machine as it is for human-driven missions, probably even more important. This is because our system will also be mass-produced. So if there is some policy that needs to be fixed, then it has to be easily fixed. Then we knew that our system, since it is a defensive system, that it must be able to continue to operate at least for some period of time, even if communication links are broken. And finally, during our meeting, we listed some of the responses our system might utilize against invading drones. We characterized the types of attacks as individual units and organized swarms. We characterize two types of missions that our system would be given: a monitor-only mission, and one where the system would actually engage the invading units. We also said that the command authority would provide a threat level that would influence how the system would respond. And we also hypothesized a set of features that our system would be able to detect. At this point in the presentation, I want to highlight that we are focusing on creating a policy that controls the behavior of our system. Our policy will assume that the appropriate sensors are available to provide the information used by the policy to make the appropriate decisions. Some of these sensors would identify features that need to be integrated to recognize a situation. This is another opportunity to use Keel technology, but we will not be walking through this process during these demonstrations today. After the meeting at CompSim, more thought was given to the idea that our system would be modular and dynamically reconfigurable. This led to the concept that the system would be made up of some number of similar, maybe even identical, Keel engines that would just be configured differently. This image, from CompSim's function block programming tool, shows an anti-access system, with the following Keel engine modules: one for spoofing, one for disrupting GPS signals, one for using a laser to blind the incoming drones, one that used projectiles to shoot down the drones, one to use nets, and one to use an electromagnetic pulse weapon. Each of these engines is separately configurable. The thought is that there would be an evaluation made by the system to determine the suitability of each approach to the observed situation. We will get into a little more detail as we look at the policy. At this point in time, we have not introduced an interlock between the individual modules, primarily because we have not determined whether or not you might want to use multiple responses simultaneously. Humans, the ultimate autonomous systems, are constantly evaluating their situations and adapting to constantly changing information in order to pursue their goals. They are constantly re-evaluating their options and allocate their available resources in the best way they can to achieve their objectives. It is the human's ability to utilize judgment and reasoning that has separated humans from machines in the past. This human capacity to utilize judgment and reasoning drove the development of CompSim's Keel technology. Keel, or Knowledge-Enhanced Electronic Logic, technology provides a way to capture and package human-like judgment and reasoning in a manner that can be deployed in machines. Judgment and reasoning are different than following rules. Rules can be processed sequentially using if, then, else logic. This method has been used by computer systems for many years, ever since computers were developed. Judgment and reasoning require information that is processed collectively, together. Note, this does not mean in parallel, or with parallel processing. With judgment and reasoning, one is balancing alternatives. It is through the use of judgment and reasoning that humans and machines can react to problems that they have never been exposed to before. Keel incorporates a value system that defines the importance of information. It recognizes that multiple factors can influence the importance of information. Keel handles decisions that might be the best decisions at one instant, but may change the next. Keel technology is made up of two primary components: the Keel engine that provides the judgment and reasoning functionality for the device, and the Keel toolkit that makes it easy to capture the judgment and reasoning concepts from a domain expert. The primary component of the Keel toolkit is the Keel Dynamic Graphical Language. The Keel Dynamic Graphical Language makes it easy to see the value system, and it makes it easy to define and visualize how information items influence other information items through a web of interrelationships. And, with its interactive nature, a domain expert can stimulate and see how information is valued and balanced. So, while it is impossible to look into a human's brain and see exactly what is considered and how all the information items are valued in making judgmental decisions, this is exactly what can be provided with Keel technology. To summarize, with Keel technology we are creating mathematically explicit policies for interpreting information, making decisions, and controlling actions that are 100% explainable and auditable. These policies are platform and architecture independent, and can be inserted into almost any microcontroller